introduced by Yanni. So Yanni will talk about multi-point vibration monitoring from a single mmWave radar system.
Okay, good afternoon, everyone. This is Yanni from Chen University in China, and I'm glad to be here to share our work, Multi-Vib, for precise multi-point vibration monitoring using the mmWave radar. So actually, vibration monitoring is not a new topic, but what we focus on here is for the multi-point part. Because we witnessed that there is an increasing number of large-scale machines and structures due to the rapid development of smart manufacturing and also the Industry 4.0. So to fully understanding the whole work of the large machine or structure, we need to simultaneously monitor the vibration of multiple points. So that's our work is doing. And also, of course, there have been some existing approaches that you all know, like accelerometers, laser vibrometers, and RFID technologies for vibration. But they have certain limitations for multi-point deployment. For example, they are tedious or costly to use when you need to monitor multiple points at the same time. And also, some technology also suffer from the low precision limitation, especially for extremely tiny vibration in the industry scenario. So that's why we propose the mmWave-based approach, and it has two benefits. The first one is that the mmWave signal has very small wavelength, so it provides a higher resolution to sense the tiny vibration, and also it has the spatial sensing capability, so it has the potential to monitor multiple points. For example, on the figure that there are 3 points and you can monitor it separately. So ideally we want to do this. So why not do some preliminary experiment to see whether it works? So we pick up a wind generator. So it has two components. One is the motor and another one is the wind box. And ideally, we want to detect these two parts separately. But according to our preliminary results, we only have one object detected. And according to the location, it corresponds to the motor. So we are thinking about why we miss the detection of the wind box. And we can look at in another perspective. So because the motor is perpendicular to the radar, so the transmitted signal can directly reflect back to the radar. So you can receive a higher strength of the signal reflected by the motor. But for the wind box, most of the signal transmitted to the box are reflected away from the radar. So the key problem is that we cannot receive the sufficient amount of signal from the wind box. So we look into the equation of the received signal strength. And we found that several of the parameters like transmitted power and antenna gains and wavelengths, that's the thing that is already settled, so we cannot change it. But we found there is a parameter called sigma, and sigma refers to the radar cross-section, RCS. And RCS is actually a measure of how easy you can detect the object by the radar. So we take a look at the RCS, and we found that there is several key factors like the project cross-section and the signal reflectivity. And the first two factors actually are determined by the object size, shape, and the material. So we cannot just change the form factor of the object, but we can do something on the last factor, which is called the signal directivity. So actually, signal directivity means the amount of signal reflected back to the radar's direction over uniform directions. But for most of the common forms of objects, for example, sphere, cylinder, and plate, they all have a relatively low signal directivity, because you can see that the transmitted signal, most of the reflect signal can reflect away from the radar, especially for the plate one. Almost all the signal are reflected away from the radar's direction. So our objective is that how can we increase the directivity? We try to solve this problem using the retroreflector. So we typically use a trihedral reflector. why it called it trihedral? Because it has 3 intersect perpendicular surfaces, and then it can cause the transmitted signal to reflect 3 times, and then the signal can reflect back in the reverse direction of the transmitted signal. And by this way, we can increase the signal directivity. And also, we make some prototype of the reflector, and you can see that by deploying the retroreflector on each part of the wing generator, you can successfully detect them separately. And in the next step, we can extract the signal of each part and use the signal phase to measure this vibration displacement. And here we also encounter a problem is that because the received signal is actually suffered from the background noises, actually it's a static vector. So we need to remove this part because otherwise the extracted signal phase is not real phase due to the vibration. So we propose a method considering the multi-antenna design, and we formulate multiple linear antenna arrays. In this way, we can have multiple arcs of the vibration, and then we can form a large arcs, and in this way, we can estimate the center, actually the end of the static vector, and then we can distract it from the signal and have a clean version of the signal phase. And in our experiments, we have designed multiple types and materials of the retroreflector, and we also use some high precision laser vibrometer or accelerometer as a ground truth. And we conduct 2 case studies, and the first one is on a conveyor machine which suffers from a misalignment problem. And you can see that we have the 2 retroreflectors, and they show different patterns due to the misalignment problem. And the error in frequency estimation is around 0.15 hertz, and the error for displacement estimation is around 16 micrometers. And another case study is performed on a footbridge. So we deploy multiple retroreflector on each step of the footbridge, and we can detect them as shown in the figure. And also we compare the signal, the accelerometer signal extracted from the millimeter radar with the high precision output directly extract from the accelerometer. And you can see that they have a relatively high similarity with each other, showing that we are also provide a high resolution measurement of the accelerometer. And finally, I will end my talk using a short demo. So in our lab, we deploy 2 motors, and we try to separately monitor them with different frequencies and vibration amplitude. And that's all for my work. Thanks a lot for your listening.
Yeah, thank you for the very nice presentation. Do we have a question while we set up? Okay, there's one question.
I think place a corner reflector on the machine is very interesting, but I have a question about it. Since wireless the one advantage of wireless sensing is contact-free, so place the corner reflector on the machine. I think this is destroys the contact-free nature. So why we directly use the contact-based sensor to sense the vibration?
Oh, I see. Thanks for your question. So, context-based sensor, for my knowledge, accelerometers is contact-based settings, but it consumes battery. Of course, you can do it in a wireless way, but still you need to long-term deployment and maintenance of these sensors. And also, in my design, in my initiative, so I want to reduce the cost for multiple settings. And the corner reflector is actually only $3 to $5 per reflector. So instead of using the relatively high cost context-based sensors, maybe my approach can be low cost. Yeah.
Okay, thanks.